I've got a great group of panelists here who, if I gave as much justice to the introduction as you gave to me, we wouldn't have time to hear from them. So I'll introduce them as we go along. First speaker is Professor Istvan Szunyogh. He's a colleague of mine at A&M. He's got his PhD from the Hungarian Academy of Sciences. And since coming to the United States, he's spent time at the National Center for Atmospheric Research at MIT, at University of Maryland, before finally coming to A&M. And he'll, like I said, focus on the weather forecasting aspect, which requires, as you'll see, a lot of concern about what's already happened before we can figure out what's going to happen.
All right. So thank you for the opportunity and the invitation to tell you about the weather. And actually, this is a great title, but it wasn't my idea. Actually, Joan gave me this, so I cannot take too much credit for that. But as you will see, and as he already said, if you really want to know what will happen in the future, you have to know the present. Can we go to the next slide? And down there is a man John already mentioned. He's Edward Norton Lawrence, who spent his scientific career at MIT. And he's the man who figured out most of what we know about how errors growing in our predictions of the weather. So basically, a numerical weather prediction model solves an initial value problem in mathematical terms, which in simple terms means that if we want to know what the weather will be tomorrow or 2 days from now or a week from now, we have to know what the weather is today. And it's not enough to have a nice satellite pictures with clouds and so on, but we really have to have a good quantitative estimate of all the parameters that describe the atmosphere. And in modern terms, you would say that the atmosphere is a chaotic system, and Ed Lawrence was one of the pioneers of chaos and chaotic dynamics, although he did his part of the research that led to this whole new field in physics long before the term chaos was coined. And for me and for people who work in the same area as me, he's probably the biggest hero of the history of meteorology. If you would ask my American colleagues who is the biggest hero in the history of meteorology, probably most of you in the United States would say Drew Charney, who was an MIT professor too. If you would ask your European colleagues, they would say it was Carl Gustav Rossby, who became famous in Sweden and who also died in Sweden. He worked late in his life in his native Sweden, but in between he came to the United States and, for example, started the atmospheric science program at MIT. And actually, he has the distinction that he's the only atmospheric scientist who has ever made it to the cover page of the Time magazine. Okay, and former Vice President Al Gore doesn't count as an atmospheric scientist. So let's go to the next slide. So what's the implications of chaos and the sensitivity to the knowledge of the present state for forecasting? So what I drew there is basically a typical evolution of the forecast error. So basically we have the forecast time on the x-axis down, and we have a measure of the forecast error on the y-axis. So what you see there, that we have a very small error initially, but that error then starts growing exponentially, very fastly, and at one point we will pass the level where there is less information in this forecast than in the climate forecast. Okay, so beyond a certain limit, the best option you can do if you are interested in what's the weather in Houston, you just go to John and ask him as the state climatologist, what's the typical weather on 10th of July, let's say. And that's it, that's the best you can do. And actually, if you run your model beyond a certain time, you will get a worse answer, because basically what you try to do, you try to forecast details that you cannot forecast. So let's go to the next slide. And I think there is a slide which is missing there. Did we jump on? Oh yeah, no, go back. I reorganized my slides a little bit. So basically there is a bad news and a good news there. So the bad news is that forecasting beyond a certain time limit is basically impossible. For the northern hemisphere mid-latitudes, and we really live on the edge of that, the southern edge of that, it's about 2-3 weeks. Beyond 2-3 weeks, we cannot say anything. But as you will see, typically beyond the week, there is not much very useful information. So that's a bad news because we have some limitations. But the good news, if we can make small improvements in the knowledge of the initial state, of the estimate of the atmosphere today, then we can make actually quite significant improvements or increases. We can buy time in forecasting down the road. So we can go to the next slide. And basically the process, what we do to try to figure out what's the state of the atmosphere today is what we call data assimilation. And data assimilation does a lot of things. It filters the noise from the observations. Because if you all learned physics at one point in your life, and you know that the way we learned about physical systems and the state of the physical system, that we make measurements. But the problem is that when you try to make measurements for the whole atmosphere, and for all the parameters that determine the state of the atmosphere, we would have to take infinite number of observations. And you will see that we almost take infinite number of observations, billions of observations every day, but still not enough. Okay, so what we have to do, we actually have to propagate that information, both in space and time, what we have. And as you will see, what is really important that we can use the models not only to do the prediction, but actually to get the estimate of the state at the current time. Because the model is nothing else than a collection of our knowledge of the quantitative laws of the atmosphere that govern the atmosphere. And basically what we can do, we can expose the data to that knowledge and try to make sense out of those observations. And if you are in oil exploration, what would come closest to data assimilation is what you call inverse problem. Because once again, when you do oil exploration, you would try to figure out what the structure of the top layer of the Earth. And what you can do, you can basically send down sound waves, and from the sound waves you try to figure out what you find down there. You cannot go there and do direct observations of the structure of the Earth. And it's also statistical interpolation, which means that we will never have a certain answer. We have errors in all the sources of information. There are errors in the observations, and actually you would be surprised that when it comes, for example, to satellite observation, how big those errors are. The real value of those observations that we have many of them. And what is really nice in estimation theory, that if you have an observation, even if it's very inaccurate, but we know the error statistics, we can always add that observation to make a small improvement. So if you have many of those observations, which are not super accurate necessarily, you can still make a huge improvement in the estimate of the state. But there will always be an uncertainty. And let's go to the next slide. And just to get a sense of how many observations actually we have, the panel I really want you to focus on is the one on your left, which basically shows the daily satellite and radar observation count for the National Weather Service of the United States. This comes from a talk from one of their former directors, who was actually the director at the time. And if you look at that graph, the first data point is 1990, and the last one is a projection for 2015. You see that we went basically a decade from 1990 to 2000, where we had nearly 1 million observations. And then suddenly we had a huge jump in the number of observations. In a couple of years we went to 100 million. And now we are at a level where we have 100 billion observations. So I told you, we are getting closer to that infinity. And what we have to do, and we do it, we have to use these mathematical models and our supercomputing powers, tens of thousands of processors, to try to come up with a quantitative estimate of the state of the atmosphere. And that's what we will feed into the computer model to get the forecast. And basically all the TV meteorologists or the professional users you may have to deal with are looking at the products. The raw product is the forecast from these models. And let's go to the next. And this is a graph which requires some explanation, but it's not that bad. What I'm trying to show here, I know it's scary for the first slide, but what I'm showing here, this is a figure from the European Center for Medium-Range Weather Forecasts, and they are considered the top weather forecasting system right now in the world. And basically, what this figure shows, you can see it shows the years on the x-axis. So the graph starts at 1981, where actually when this forecast center was started, when the Europeans started preparing these forecasts, and then the different colors refer to a different forecast range. So the blue on the top, that refers to the 3-day forecast range, the red refers to 5-day forecast range, and the green refers to the 7-day forecast range, and the yellow refers to a 10-day forecast range. And the top of each of those colored areas shows the quality of the forecast for the northern hemisphere, and the lower one for the southern hemisphere. And what you see there is, and this number can change from 100 to, it can change between 100 and 0, but the usual assumption is that when the value drops below 60, there is not much value in the forecast anymore. So basically, what you have to see that everything that is below the 60% line is a useful forecast. That's what it shows, that at that time range, the forecast is not good. And it basically says that typically the 10-day forecast is not that great. But the shorter term forecast actually do have a scale. And what you see on this curve, how much that scale improved from the past, from 1981 to the current time. And another very important feature I would like to point out, that if you look at the turn of the millennium, you may remember that that's when we had that huge jump from an order of 1 million observations to 100 million observations. Actually, that was the point when we started to figure out how to use satellite observations for this kind of quantitative forecasting. And you really see that that's where there's a big jump, because we became much better at determining what's the state of the atmosphere. And the other thing what you can notice, that there is not much difference between the northern and the southern hemisphere. And the one very important difference between the northern and the southern hemisphere, that most of the southern hemisphere is ocean. So in the old days, when we had ground-based observing system, we had very, very few observations there. Basically, most of the information on the southern hemisphere comes from these satellites. And you can see once we figured out how to do it mathematically, we had the satellites there, we basically can do, in our days, just as good forecast for the southern hemisphere as for the northern hemisphere. So, my part.
Thank you.